Laser diffraction. Aim: conduct an experiment to determine the size of the micro-dimensional system by using the laser beam diffraction. Here the micro-dimensional system we are using is a single slit. Apparatus: optical bench consisting of a diode laser source, single slit, screen that is a graph paper, and a DC regulated power supply. The size of the micro-dimensional system or the width of the single slit is given by the expression E is equal to plus or minus n lambda by sin theta, where n is the order of diffraction minima, theta is the angle of diffraction, lambda is the wavelength of the laser source used, that is 6350 angstroms. Plus or minus sign signifies that the minimas, the diffraction minimas are formed on either sides of the central maximum. This is the model diagram for the experiment, and this is the monochromatic laser source, and this is a single slit, and these are the diffraction fringes formed on the screen. In the place of screen, here we are using a graph paper for recording the diffraction pattern, and here the block here shows the diffraction fringes. Here 0 indicates here the central maximum, 1 and 1 here, 1 and 1 on either sides indicates the first order principal maximum, 2 and 2 indicate the second order principal maximum, which are formed on either sides of the central maximum. And this is the diode laser source of wavelength 6350 angstroms. This is the micro-dimensional system. Here we can observe that, and this is single slit. In the place of micro-dimensional system, we are using a single slit whose width should be determined here. And this is the screen. In place of a screen, here we have placed a graph paper where we are going to record this diffraction pattern. Now these components are all arranged on an optical bench. Switch on this IC regulated power supply, and now the laser beam is now striking this single slit normally, and this laser beam will start to diffract, and this diffraction pattern can be observed on the screen. This is a graph paper. Here in this diffraction pattern we can observe the diffraction fringes here of different orders. This is a central maximum or the maximum of highest intensity which is observed at the center of the diffraction pattern, and these red spots on either sides will indicate the different orders of secondary maximum. So this is the first order secondary maximum, this is second order secondary maximum, third order secondary maximum, and so on. Again, in a similar fashion, on the other side also you can observe this first order secondary maximum, second order secondary maximum, and third order secondary maximum on the other side also. You can observe that the intensity of the secondary maximas is gradually going to fade off with the increase in the angle of diffraction. We can observe that, but the central maxima appears to be of highest intensity. Now we can observe another point, that in between any two maxima you take, in between any two maxima, there is a minima that is situated exactly at the center. This in between these two maxima also we can observe a minima that is situated exactly at the center. Minima means zero intensity. You can observe that there is no light spot here, so it is a zero intensity region. Similarly, such minimas are observed on the other side also, in which the first minima appears between central maximum and the first order secondary maximum. This middle position is the position of first order minima, and this is the position of the second order minima. This is the position of the third order minima and fourth order minima, and so on. On other side, the minimas of minimas of different orders on the other side of this pattern, that is this side of this pattern, can also be observed. Here this corresponds to the first order minimum. Here this is the position of the second order minimum. This is the position of the third order minimum, fourth order minimum, and so on. The distance between slit and screen can be measured here on the scale provided in the optical bench. In our case, it is observed to be around 100 centimeters. Now this is the diffraction fringe pattern recorded on the screen or the graph paper. Now here in the diffraction pattern, we can observe that these two fringes correspond to the first order minimum on either sides of the central maximum, These two diffraction fringes indicate the second order minimum on either sides of central maximum, and these fringes indicate the third order minima on either sides of central maximum, and the other fringes correspond similarly to the fourth order and fifth order fringe patterns, minimas on either sides of this central maximum. Now measuring the distance between these two, the position of these two first order minima fringes, we'll measure it on the graph paper and divide this total length by 2. Then we get the position of the first order minima from the central maximum, that is small y, and it is written over here. And similarly we measure the distance between the second order minima fringes on either sides of this central maximum, and we divide it again by 2. We get the position of the second order fringe from the central maximum. Similarly we repeat this process for all the fringes, and these values are tabulated as shown in this table. So for sample I have written the second order fringe, second order minima is falling at a distance of 0.65 centimeters from the central maximum, and the third order minima is falling at a distance of 0.85 centimeters from the central maximum, and the fourth order minima is falling at a distance of 1.1 centimeters from the central maximum, and similarly the fifth order minima is falling at a distance of 1.35 centimeters from the central maximum. Here next we calculate the sin theta value. Now we calculate the sin theta values correspond to the various orders of minima. We can observe the second order, for second order minimum the sin theta value is 0.0065, and for third order minimum it is 0.0085, and the fourth order it is 0.11, and the fifth order it is 0.0135. Here we have calculated the sin theta values based on this formula y by root over y square plus L square, where y refers to the position of the minimum from the central maximum, L refers to the distance between slit and screen. So we already observed that L is 100 centimeters, we measured on the observation on the optical bench, and y values we have here, we have the y values here for different orders of minimum. So we calculate the sin theta values. Next, using the sin theta value, we will calculate the width of the single slit or the width of the micro dimensional system E by using this formula, that is n lambda by sin theta. Lambda is the wavelength of monochromatic laser beam, that is 6350 angstroms. We will convert that value into centimeters and substitute sin theta value. N is the order of minimum, first orders, second order, third order, fourth order, fifth order. For different orders we are having different E values. We have calculated that, and we will measure what is the total average value, and we will get it around 0.022 centimeters. Now the precautions for the experimenter: we should avoid the direct eye contact with the laser, and laser should be operated at a constant voltage of 220 volts, so to avoid the flickering of the beam.